An important skill in physics is distinguishing between closely related concepts. We've already distinguished between velocity and acceleration. Now let's distinguish between two other closely related concepts, mass and weight. Maybe you've been hearing about the source of mass, the recently discovered Higgs boson. Yum stuff. But first, you'll want to understand mass in its simplest sense. Phil Physiker defines mass.
Mass, the quantity of matter in an object. It is also the measure of the inertia, or sluggishness, that an object exhibits in response to any effort made to start it, stop it, or change its state of motion in any way.
Mass has to do with the laziness of matter, the inherent resistance to changes in motion. But how about weight? How is it different? Weight is force, how hard something is pushed or pulled. But what kind of force? Often weight is defined as gravitational force. Then we write weight equals mg. Weight is mass times a constant called g, which turns out to be the acceleration of gravity. We can see this by using Newton's second law for an object acted on by gravity alone. From F equal ma, we get mg equals ma, so A equals g. All objects fall freely with the same acceleration because the force of gravity is proportional to mass. Large mass objects experience a lot of gravitational force. Small mass objects experience little gravitational force. That's why it's easy to confuse mass and weight. But remember, an object carried to the moon will have less weight there, but the same mass. An object floating in remote space will have no weight at all, but it will still have the same mass as on Earth. This leads to a new definition of weight that is appropriate for this space age. According to Phil Physiker,
Weight, the force with which an object presses against a supporting surface, or, if suspended, in a supporting string. The weight of an object is often, although not always, due to the force of gravity.
think of a fighter pilot who sits on a weighing scale in his cockpit. When at rest or flying in a straight line at constant velocity, the scale reads the same as at home on the bathroom floor. But if he enters a sharply banked curve, the scale reads more, maybe 3 or 4 or 5 times more. The pilot literally weighs more in the sharp turn because the seat supplies a greater support force. If he carries the scale with him for a vacation trip to the International Space Station, the scale there will read 0. He is literally weightless. But always he has the same mass. Weight and mass are often confused, so let's drop into my conceptual physics class for a demonstration that highlights the difference between weight and mass. Here's a ball hanging by a string. Here's another string here. What I'm going to do is I'm going to pull the ball harder, 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 and snap. One of those strings is going to break. You got to be guessing which string will break. We'll get the scene like this. Okay. I pull down, pull down, pull down. Which string breaks, this one or this one? Check your neighbor. Take a guess. How many be saying, it's the top string gonna break because he's got the other one over here for the next trial? Let's try it, gang. Here we go. It was the top string. HC. How come? Let's look at it. When I pull this down, don't I set up a tension in this string here? And doesn't that tension also transmit it up to here? So don't I have that tension in both strings? Huh? Isn't that true? So it could be either one. Maybe sometimes it'd be the bottom, maybe sometimes the top. Except for what with the ball? Its weight or its inertia? Begin with a W. End with 8. Try it. Weight.
the weight of the ball acts on which string? This one or this one? This one. So on the top, you have the weight of the ball plus the tension of pulling, and over here only the tension, so sure enough, the top one breaks. Okay? Shall we try it again? I'm going to whip the string down very, very quickly. I'm going to ask that ball to accelerate more than 10 meters per second, because I'm going to, boom, get down like that. Not slowly like before. And watch what happens. Sure enough, the bottom string breaks. Ain't that nice? See that, huh?
Back to our screencast. In summary, the weight of the ball produced a tension mg in the top string in both cases. When the bottom string was pulled gradually, tension buildup in the lower string transferred to the top string, making tension there the sum of the two tensions. Hence the top string with greater tension broke. Weight in action. But when the lowest string was whipped downward, the ball's inertia played the dominant role in not moving with the sudden downward motion, which allowed the bottom string to break. Inertia in action. I want to leave you with a question. If you want to tighten a loose hammerhead onto its handle, it's a good idea to slam the bottom of the handle against a firm surface as shown, rather than the other way around. Is it gravity or inertia that accounts for the hammerhead sliding a little farther down on the handle? HC, how come? Until next time, good energy.